Welcome to Microfluidics 1. Today we are talking about different simulation approaches that are useful in microfluidics. I think most of you already encountered simulations in your studies. On the right-hand side, you can see two different simulation outcomes. The first one is a classic CFD simulation where the flow around a cyclist is calculated. And in the lower half, you can see a microfluidic mixer where two different liquids depicted in red and blue are mixed. And what is illustrated is the species concentration. As you can see in those quite different examples, simulations are useful for a variety of different questions, ranging from fluid flow to questions of mass transfer or heat transfer. After today's lecture, you should be able to state the basic principles and potential use cases of the three general simulation approaches. You can explain the basic concept of computational fluid dynamic simulations. You can use the system-level network approach to construct equivalent circuit diagrams for microfluidic networks. And you can reason if a system-level network or a classic CFD approach is suited for a specific application. In this course, you're going to watch 4 different videos. In the first video, which you're watching right now, I give you a short introduction to the topic. The second video deals with particle-based methods. In the third video, we are quickly discussing mesh-based computational fluid dynamics. And in the last video, we are taking a detailed look at the system-level network simulation approach. Those videos will be complemented by 2 different examples where we take a deeper look at 2 of the different approaches. When you tackle a problem using modeling and simulation techniques, the general approach, how you solve or analyze a problem, does not change. This process or this approach is illustrated on the right-hand side. But of course, the usage of modeling and simulation techniques has an impact on the different steps of this workflow, which we are quickly going to discuss. The first step that is influenced if you use modeling and simulation techniques, of course, is the modeling step. Using simulations allows you to model systems with a higher complexity, as you're not required to solve the governing equations by hand. The mathematical description, of course, also has to be adapted for a numeric approach. And this is due to the fact that computers solve equations differently than a human does. So whenever you use modeling and simulation techniques, please be aware that you might need to change the mathematical description of your problem. And the solving, of course, is done numerically, and due to this fact, you have to keep in mind that numeric methods are convenient, but they usually introduce numeric errors. And this makes the verification step, which is done in the post-processing, very important, because numeric errors can sum up. And in general, it's not only the verification you need to take seriously, but also the validation step. So once you're done with modeling and you have the results of your simulation, always make sure that you do the verification and especially the validation. As the modeling is such a crucial step, I would like to discuss some aspects of modeling when working with simulation approaches. The first aspect you have to think about is what physical effects you want to include in your model. So those physical effects could be fluid flow, heat transfer, or chemical reactions. But of course, it's not limited to those 3 examples. So depending on your application, there are other effects you might want to consider. And then you have to determine your model geometry and all the parameters. And this includes the shape and size of the system, of course, or the material properties of your system. And once that is set up, you have also to think about the initial and the boundary conditions. And this is really important because even if you identified all the relevant physical effects, and then you did a very good representation of your model and you modeled everything very accurate. And if you then choose wrong initial conditions or unphysical boundary conditions, you will end up with a completely meaningless result. So the correct choosing of initial and boundary conditions is really important. As you're typically limited in your resources, you also have to think about simplification. So before you start any simulation, you should again think what physical effects can be neglected or which geometrical features are really relevant or can be simplified. You typically want to simplify your model for various reasons. One, of course, is that the validation of an easier model is, of course, also easier. And the second one is that you're typically limited in resources, and the more complex your model are, the higher are the resources you need for simulating your model. The last aspect is the mathematical formulation of the model. This is usually done in terms of partial differential equations, or it can be ordinary differential equations, for example. And the quality of the mathematical formulation determines the numeric accuracy. And yeah, this again is a little bit the verification part, where you have to take account for numerical errors. And we are also talking about this in one of the examples in the lecture. And to sum it up, the modeling is an absolutely crucial aspect for any simulation approach. And if you ever do modeling and simulation, please take care to very, very careful model your problem. So today we are talking about 3 different simulation approaches. And I would like to give you a quick overview about the basic features of those approaches. And we start with the particle methods. And in the particle methods, which includes, as you can see on the right-hand side, molecular dynamics, those particle methods are a bottom-up description of transport via individual particle motion. That means individual particles are resolved. And as you can see on the right-hand side, those methods are typically used when you have a small length scale of your problem and a short time scale. So if you want to study a problem in detail. The next method or group of methods are the mesh-based computational fluid dynamic methods. In those methods, partial differential equations for the macroscopic variables, for example, pressure or velocity, are solved on a grid, usually on a mesh. So all those methods are based on the continuum assumption. And as you can see on the right-hand side, those methods are used when you have a longer time scale to simulate, or if your problem is a little bit larger. So for example, if you simulate a nozzle as indicated here, so this is an inkjet nozzle, and if you want to simulate how the drops form in that nozzle, you would usually use CFD. And then the last group of simulations, or the last approach, is the system level network simulation approach. And here we have equations for macroscopic variables, meaning, for example, pressure or volume flow at discrete points in the network. So you can see it already here. It looks a little bit like an electrical circuit network. So this approach is quite useful to study the interaction of system components. And therefore, of course, this approach is usually chosen if you either want to simulate a very large time scale, or if you have a quite complex and large system. So it can cover a lot of applications, but it's not as detailed as the other approaches. So all of those different methods have their potential use cases, and all are used, but they differ fundamentally. And we are going to discuss this in the following videos.